So let's move on and give you some examples of these augmented maps. Remember my bullet, we had maps augmented with other devices, and then we'll see what these could be. Let's just start with the basics, and the basics is just a map, which is referred to as a choropleth map, not chloro. There's no chloro, there's nothing green in there. Okay, this is a map which is essentially a categorical map. So think of a distribution of data which is a continuous distribution, say, incomes or house prices or rainfall. And you want to represent the spatial distribution of this information somehow. But you can't have a continuous scaling, so you simplify it into categories. The same way you simplify a continuous distribution into histograms. So histogram is a discrete representation of a continuous distribution. You take the incomes 0 to 10,000, 10,000 to 20,000, and so on. So you simplify what was a smooth and continuous function into a step function or a discrete approximation. A choropleth map, in essence, does the same thing. So it goes from the continuous distribution to categories. And these categories then are represented by a color or a shading. And it's important to keep in mind that there's a lot of information loss that occurs in this process. There are a number of different ways in which we can do this. They involve the choice of the intervals. Just like with a histogram, you have to choose where you cut. What are your cut points? And how are you going to do that? Let's say you have a house price distribution. We have 100,000 real estate sales for Los Angeles, and we're going to represent this somehow. And they go from 2,000 to 50 million. So one thing you could do is go from 2,000 to 50 million, take that 50 million interval and cut it into 5 intervals of 10 million. So all the houses between 1 and 10 million are one color, 10 to 20 million are one color. What's going to happen is pretty much the whole map will have the same color given the distribution. So these are the kinds of things you have to think about, not do blindly. Equal interval may sound good to you, but that is completely useless when your distribution is highly skewed, because the intervals in the skewed part will have very few observations in them, and in the denser part will have just about everything in it. Natural breaks is a technique that tries to, it's a nonlinear technique that tries to estimate optimally where these cut points should be given the distribution of the data. You can think of it as some kind of way to identify gaps in the distribution. So you have a continuous distribution, but there's some gaps in there, and you try to cut in these gaps. Again, this is not unambiguous, because you have to make decisions. How many of these cut points and so on, and depending on how you do this, because you lose so much information. I mean, think about it. We potentially have 100,000 different values, and we're going to reduce them to 5 or 6 different categories. There's an enormous loss of information there, and that's something that's not always intuitive when you look at the map. You have to think about, well, what does this really represent? I see 5 different colors, but behind these 5 different colors could be a tremendously rich distribution, and they're all given the same color because of this discrete approximation of the distribution. These equal interval and natural breaks are the kinds of criteria that come out of cartography. There are other criteria that are more statistically based. For example, quantile maps are maps that look at the cumulative distribution of the data and put the cut point at specific quantiles. A quartile map, for example, would have 4 cut points. A quintile map would have 5, and so on. Another way of doing this is a standard deviational map. Now, I said, if you don't ask questions, I will start asking questions. Well, what do you think a standard deviational map might be? What is a standard deviation? It's a measure to look at how the distribution varies around the mean. So it's the square root of the variance. It's the sum, the average of the square deviation from the mean. So it gives you a sense of the spread. So what we're trying to do is to reflect this in a map. How many observations are close to the mean, both above and below, and as they get further and further from the mean, we call them outliers, right? And one rule of thumb is 2 standard deviations away from the mean. That's an outlier. That's based on a normal distribution, but it's still a useful concept. So what we can do is make a map which uses as categories 1 standard deviation. So the mean is the anchor, and you have 1 unit above the mean. That's 1 standard deviation above the mean. That's 1 color. So all the observations that are within 1 standard deviations above the mean are given the same color. And then the second unit is the second standard deviation, and so on. So once you get to the third one, technically speaking, we have outliers. Okay. And so what you could do is say, well, I take 3 and above and I put them all together because they're outliers. We don't want to have too many of these categories, so then we have 3 categories above the mean and 3 categories below the mean, so 6 colors. Speaking of colors, and I'll show you in a second an example of this map, you can't just pick any color, because again, color provides information and gives you cues. You may not be aware of it, but it affects you differentially. And there's been a lot of research on which color schemes to use in maps. And unfortunately, some of the commercial mapping packages use completely terrible color schemes that are completely inappropriate. And there's one website, it's called Color Brewer, that you might want to take a look at. And in GeoDa, we use Color Brewer colors, which are particular class of gradations of hues that can be used in Choropleth maps. And there are different kinds of maps. Maps that have a direction like this one does. We go from small to large. There are also categorical maps, and there it's even trickier to choose colors, because you don't, in a categorical map, you do not want to give the impression that one color is better than another color, because they're just categories. You know, they're single family, multifamily. You don't want to give the impression that somehow multifamily is better than single family, or is twice as important as single family, which you can easily do by picking the wrong colors combinations, where one color is seen as superior to another color, or warmer than another color, or colder than another color. And you want to avoid this kind of impression when you deal with categories. Now, when you deal with values like here, then you want to exploit the warmth or the coldness of a color. And reds and browns are warmer and tend to be used for higher values, and blues, for example, are used for lower values because they tend to be cold. Now, with red, you have to be careful, because red is like a red flag, and can have side interpretations in certain contexts. So you want to stay away to use red to represent something bad, and there's all kinds of things. I don't have time to get into this. I'm also not really an expert, but I just send you to Color Brewer, and if you stick to that, this is based on a number of very sound principles. The other thing, just as an aside, and you probably have already experienced this, is that what you see on your screen is not what you see on paper, and is not what you see on the projector. There are transformations, because colors are, to us, humans, they're pretty much continuous, but to the machine, they're not. They're discrete. And so again, there is a simplification going on that, in a sense, digitizes, makes it digital, this color information, and as a result of that, different processes will translate it back differently, and whether you see it on a screen or printed on a piece of paper will be different. And so there's software to make sure that your colors in professional printing, this is very important to make sure that the colors remain true, so that what you intended to show and what you see on your screen is in effect what shows up on the paper, and that's a whole different size to it. Now this is an example of a standard deviational map. The mean is nondescript in the middle. As you move away from the mean, it gets darker brown. As you move away from the mean in the other direction, it gets darker blue. So these dark blue and dark brown colors are actually two standard deviations away from the mean. So what does this map tell you in terms of the distribution of the data? We have the mean, and then these first categories are just one standard deviation away from the mean, and then we have two, and then these dark blue and dark brown. Outliers. What would you expect in a distribution? Think of a bell shape. Where are most observations? In the middle, right? Around the mean. Where are they here? Out. So we have relatively few observations. Now, always take this with a grain of salt, because we're cutting a continuous distribution into 6 categories. So a lot of the subtlety is thrown out the window, but for all practical purposes, what you see here is possibly a bimodal distribution. Possibly something where you have a lot of lows and a lot of highs, but not much in the middle. So if you throw them together, you may get an artifact, in that this might be a situation that I referred to the other day as heterogeneity, where you are mixing two distributions, one at the high end and one at the low end, but we're throwing them together, so we get this weird result with a lot of outliers and not much in the middle. A normal map, and I use the normal term in the sense of Gaussian distribution, would not show this. It would have the bulk of the observations, in fact roughly 95%, in the first 2 bands up or down. Okay, that's not the case here. So this is one way in which you can use a map, a Choropleth map, to get insights about the distribution of the data, but not just the distribution, which you can do with a histogram too, also the spatial distribution. Because there's another thing here. It's not just bimodal in terms of a histogram, it's also bimodal in terms of space. Remember this notion of spatial randomness. If it was spatially random, there is absolutely no reason why all these dark browns should be in the center of the town. They shouldn't be. We should get more of a checkerboard type of a pattern, with a little bit of brown here, a little bit of blue there, everything kind of mixed together, but it's not mixed. It's very stratified. And this ties back into what I mentioned the other day with the locational invariance. Okay? The information that we get from this map will change when we move these neighborhoods around. We get some information here that we don't get from a histogram. The histogram might tell us, yes, we have this maybe bimodal distribution, but they won't tell us that one group is in the center of the city and the other group is at the outskirts. That's spatial information. Okay. So what we're trying to do with these statistical maps is to get more and more sophisticated in terms of the types of insights that we can get by combining these maps with specific graphs and other devices. Continuing along the same theme, focus on outliers is very important. Outliers are very interesting observations because they tell us that something is not right. Now, what is it that is not right? That we don't know. It could be a data error, and oftentimes outliers are coding errors. Somebody inadvertently put a couple of extra zeros behind the price of a house, and you have a $50 million house in a market where everything else is 100, 200,000. Right? That happens. Now, to see this in a table of numbers is hard. I mean, some people are better at it than others, but it's basically difficult. To see this in a graph is easy. You spot them right away. And so the idea of an outlier map is to use the same rationale as in a graph to spot outliers, but to move it to a map. And one type of outlier map that we will use a lot, because I happen to like it, is what I call a box map. And a box map is the spatial representation of a box plot. Now, technically a box map is only non-parametrically. So it would not deal with standard deviations, but with the other thing you mentioned, the quartiles. So it's not the mean, but the median is the anchor. And then you take the quartile below and above. So the first and second quartile, let me show you a picture here, if it's not very clear, but this is a cumulative distribution, and what it shows you, each of these little points is an observation in the distribution. So we go from the minimum all the way up to the maximum. It's a cumulative distribution of the observations, but scaled so that you see how far apart they are. And if we take a non-parametric approach, we can put important breaks at the first 25 percentile, the median, which is the middle, the point where exactly half is below and half is above, and then the third quartile. And a counterpart to the standard deviation in parametric statistics is what is called the interquartile range. And the interquartile range is the difference between the third quartile and the first quartile. Now, the difference in value, okay? So we're basically sorting all the observations from lowest to highest. Those are all these dots on the graph here. And so when we reach 25%, we draw a line, and the value for that observation is the first quartile. When we reach the midpoint, we draw a line, and the value is the median. The difference between the value at 75% and at 25% is called the interquartile range. It gives you a sense of the spread around the median. And what we do then is take this and multiply it by 1.5 or by 3. This is fairly arbitrary. Actually, the 1.5 comes from the parallel with the normal distribution, where you have the two standard deviations capturing 95% of the distribution. So that's the rationale behind here. So you take this interquartile range, which is this vertical distance on the box here, multiply it by 1.5, and then we have this bar, which is called a fence. And everything above the bar, these are yellow. It's not easy to see them, but they are yellow. These are called outliers. And everything below the bar, in this case there isn't anything, would also be called an outlier at the lower end. So it's a very simple idea. It doesn't assume anything about the distribution. It takes basic descriptive statistics of central tendency, the median, and spread around the central tendency, the interquartile range, and uses that to identify extreme values. Now, extreme, why do we say these are extreme? Because what we're thinking really is, do these observations belong to the same distribution? If we have too many very high values and too many very low values, think back of our bimodal setting, then maybe what we're doing here is mixing observations together that do not belong together. And why is this important? Because in the end we're trying to explain or model what we observe. And if we explain a mixture of two processes by one process, we're going to be wrong. This is the example of the fridge and the stove. You model the middle, there is no such thing. It doesn't exist. Okay, you should model the stove and model the refrigerator. So this is one way among many to try to detect situations where this may be the case. If you have too many large values or too many low values, something might be going on that makes these observations different from the rest. Why? We don't know. That's a different story. But identifying these interesting patterns is what we try to do in an exploratory analysis. Now, what is a box map? The box map is the counterpart of this in map form. And why do we want to do this? Because we want to exploit the spatial information. Let me just get back to this example. This is a map and a plot of the results of an election, as it happens in Argentina, in Buenos Aires. So we find, doing this analysis, we take the interquartile range, we get our fence, we get all these yellow dots on the top of the box plot, or the box and whisker plot, that we identify as being outliers. From a non-spatial perspective, that tells us these may be different. Right? From a spatial perspective, a priori, we have no reason to think that these would be organized in any systematic way. Now, what the map shows you is that they're all here, which is highly unusual. I shouldn't really say this because we haven't done any tests or anything like that. But the chances that these outliers are all in the same spot and are there by chance are extremely low. So what this tells us is, again, it's one of the many ways in which we will get at this question. This tells us this is not spatially random. There's something going on here that might cause, remember the cause and effect thing, might cause these people who vote in these wards to live in this particular area. Maybe they have the same religion, maybe they speak the same language, maybe they come from the same region, or same socioeconomic characteristics, which are then possible explanations for the reason why they vote this way. Okay, so these are the votes. I forgot which one this is in particular. This is an election in '99, and this gives us the percentage of the vote for one party in that electoral ward. So it's aggregate, right? It's not disaggregate. We talked about ecological fallacy last week. This is one example where you have to be very careful not to fall into that trap. Because what we can say later on when we do the regression is we can try to relate these voting results to characteristics of these wards, not the people, the wards. So then we can say that wards that tend to be, say, predominantly Catholic tend to vote predominantly for this party. That doesn't mean that all Catholics vote for that party. That would be an ecological fallacy, because we don't know at the ward level how they mixed. We just see that this is a ward with more Catholics than the other wards and more votes for this party than the other votes. And so we could put two and two together at that level, but not below, where we cannot say that the Catholics voted for this. I mean, we can, under certain, don't take me wrong, sometimes you can make that statement, but not with this level of information. You need more information. Okay? But the interesting part of this is that the observation of the outliers in terms of the distribution of the attributes, if you wish, now gets coupled with an observation on the location of the outliers. And this provides additional information. This is what I refer to as added value. If you didn't have this left-hand side of the picture, if you didn't have the map, you would not know that all of these are in the same area. And then you can, of course, push this further and see, well, what's special about this area? What are the characteristics that make these particular electoral wards similar? And that gets you then towards certain hypotheses about who votes for who, or other phenomena like that. So this is the box map, just to go back to the presentation, to the bullets here. So we use the same criteria as for the standard box plot to identify the outliers,